Hey there, and welcome to this explainer. Let's jump right in, shall we? Modern cars are just not the mechanical beasts of steel and oil they used to be. Not anymore. Today, they're essentially highly complex, multi-million-dollar software platforms rolling around on wheels. We're talking about massive, intricate digital ecosystems that require incredibly rigorous bench testing to make sure they are totally safe and reliable. So today, we're going to put on our tester's lenses and see exactly how these systems are validated long before they ever hit the dealership lot.
Just think about the question we have right here. It's a pretty terrifying thought, right? What actually happens when a software update bricks a car in your driveway? This perfectly highlights the incredibly high stakes of automotive quality assurance testing. Look, if a traditional FM radio fails, well, that's annoying. But if a telematics update fails or a core system crashes while you're cruising down the highway, that is an absolute disaster. The engineers running these tests are literally the ultimate guardians of both the driver's safety and their convenience. So here's our roadmap for peeling back the layers of a modern vehicle's digital anatomy. First, the smartphone on wheels. Second, the car's nervous system. Third, media and phone integration. Fourth, navigation and smart routing. Fifth, telematics and OTA updates. And finally, number 6, finding and fixing bugs. Let's get to it.
Starting off with Section 1, the smartphone on wheels. We're going to take a top-down look at the infotainment head unit.
And that journey begins with just turning the vehicle on. There are 4 highly distinct ignition modes to test. First up is state 0, or off. But for a tester, off definitely doesn't mean 0 power. It means testing for a deep sleep state. Then we have state 1, accessory. Here, testers validate power management, basically making sure you don't completely drain your battery just by listening to the radio. Next is state 2, run. This is where every computer is awake and talking, and testers check that certain features, like video playback, are strictly restricted if the car is physically moving. Finally, there's state 3, crank. This is literally the most violent electrical moment for the car. The starter motor engages, and the voltage just plummets. Testers have to ensure the infotainment system survives this violent drop without a hard reboot or any weird audio distortion.
Now, speaking of that off state we just mentioned, take a look at this number, 10 milliamps. This is an absolutely crucial dark current limit. If the head unit fails to enter deep sleep and stays awake, drawing anything more than 10 milliamps in that off state, the driver is going to wake up the next morning to a totally dead 12-volt battery. Not a great way to start the day, right? So a tester's job is to ensure that the current drops below this exact threshold within 2 minutes of turning the key off.
Moving on to Section 2, the car's nervous system. Let's look at the raw data flowing through those copper wires.
So what native languages do the car's computers actually speak to each other? The first one is CAN, the Controller Area Network. Think of CAN as the car's internal highway. Unlike the regular internet, which routes things using IP addresses, CAN is totally message-based. Every electronic control unit, or ECU, sees every broadcasted message on the network. They decide whether or not to listen based on ID priority. And here's the kicker. Lower CAN IDs always win the arbitration. This is a brilliant setup because it ensures that critical safety systems, like the brakes, always have a lower ID. They will instantly override something trivial, like your volume knob.
But as cars get smarter and far more complex, that highway naturally needs to be way faster. Classic CAN handles about 1 megabit per second, but then we have CAN FD, which stands for Flexible Data Rate, and that pushes up to 8 megabits per second, carrying much larger 64-byte payloads. Testers absolutely rely on this faster speed. They need it to handle the massive data payloads of modern over-the-air updates, not to mention the complex sensors used in advanced driver assistance systems. Classic CAN is just way too slow for the cars of tomorrow.
Next up is UDS, or Unified Diagnostic Services. I absolutely love this quote from our sources. If CAN is the highway, UDS is the specific set of commands used to interview an ECU. This is essentially the mechanic's language. QA engineers use specific hex codes here to get things done. For example, they'll send UDS service 0x19 to read fault codes and figure out exactly what's broken. Or they might use 0x27 to test cybersecurity protocols and securely unlock the ECU before making any programming changes.
All right, Section 3, media and phone integration. Let's shift back up to the driver's perspective.
How exactly does the car transition from a standalone computer to a remote display for the smartphone in your pocket? Well, when testing systems like Apple CarPlay and Android Auto, testers look at both wired and wireless integration. For a wired connection, they're heavily measuring the handshake, meaning does the icon actually appear on the screen in under 3 seconds? But wireless integration, that is the future.
Here, an initial Bluetooth handshake tells the phone to switch over to a high-speed 5 GHz Wi-Fi channel so it can stream the video straight to the dash. To test this thoroughly, engineers simulate incredibly noisy Wi-Fi environments right on the bench to see if the map pixelates or starts lagging out.
And this breakdown brilliantly illustrates some of the industry showstoppers that QA engineers are constantly hunting for on the bench. Take a ghost USB, for instance. This happens when the screen still shows a device that was already physically unplugged, simply because the system completely missed the on-mount signal from the kernel. Then there's audio echo, where callers hear themselves during phone calls because the car's echo cancellation tuning totally failed. And my personal favorite, resume failure. This is when you get back in your car and instead of your USB playlist resuming, the radio just blasts static. Why? Because the USB hardware took too long to spin up from deep sleep and the software basically just gave up waiting.
Now for Section 4, Navigation and Smart Routing. Time to look at the brain of the vehicle. Yep, 100 gigabytes. That is the massive size a fully onboard map database can reach on a car's internal drive. Testing GPS isn't just about satellites. It involves a complex mix of dead reckoning sensors and real-time cloud data. Testers have to rigorously validate this massive local storage so the car can still navigate perfectly even if you're stuck in a concrete basement with zero cell service. On the flip side, they also test off-board streaming maps to measure latency and see exactly how the system handles dropped cloud signals, making sure your screen doesn't just go totally blank the second you lose 5G. But consider this. What happens when the map needs to talk while you're blasting your favorite music? That is called audio ducking. There is a highly complex audio matrix arbitration logic at play here. Testers have to verify that a high-priority navigation prompt, like "turn right in 100 meters," seamlessly lowers the volume of your secondary Spotify Bluetooth stream. They also test out extreme edge cases, like ensuring a critical nav prompt doesn't suddenly get cut off or cause a massive echo if you happen to be on an active hands-free phone call. Moving on to Section 5, Telematics and OTA Updates. We're journeying into the hidden umbilical cord of the car. We're talking about the Telematics Control Unit, or TCU. Inside this unit, you'll find some highly specialized hardware that keeps the vehicle online 24/7. You've got the 4G/5G network access device and an EUIC SIM that actually lets the manufacturer switch cellular carriers entirely via software. What's really fascinating here is the internal battery. Think about it. Even if the main car battery is completely destroyed in a bad crash, this tiny internal battery kicks in to power an emergency 911 e-call. It uses the GNSS module to automatically send first responders your exact coordinates, and it even enables background tracking if the vehicle is ever stolen. Pretty wild, right? The TCU is also the brains behind over-the-air or OTA updates. This whole process is a beautifully complex multi-stage orchestration. First, the car pulls the server for updates. Then it downloads the package to a secondary AB memory bank, strictly verifying all digital signatures to prevent any hacking attempts. Next, it checks preconditions, like making sure the battery level is high enough before it finally installs. And let me tell you, testers are absolutely brutal here. They will intentionally cut the Wi-Fi halfway through the download or suddenly drop the bench voltage just to make perfectly sure the car safely rolls back to the old software version instead of just dying right there on the spot.
And that brings us to our final part, Section 6, Finding and Fixing Bugs. Let's see how they actually catch these show-stopping errors.
So, what tools do they use? Well, they rely heavily on the DLT viewer, which stands for Diagnostic Log and Trace. You can think of this as the standardized automotive black box recorder. When you got an infotainment system with hundreds of different components all trying to communicate at the exact same time, the DLT viewer captures every single system event, error, and user interaction in real time. It literally allows testers to see line-by-line code execution. This turns what would normally be a vague guess about a broken USB port into a highly solvable, concrete puzzle for the software developers. Now, to actually make sense of all that data, testers rely on log urgency levels. At the top, you have fatal logs, which track massive system-ending crashes. This filters all the way down to info logs, which might just track a high-level system narrative like a user switching menus. But when a tester is hunting down a really complex elusive bug, they drop straight down to the debug and verbose levels. Because this granular tracking generates thousands of messages every single second, they use application IDs, like filtering strictly for the media player, to isolate the exact root cause of a multimedia or connectivity failure. And once they finally find that bug, they apply the absolute golden rules of test engineering, known as the 3 Rs. First, reproduce. Can you trigger this exact issue 3 times in a row? Second, refine. Isolate the variables, for example, noting that the bug only happens when Bluetooth is also actively connected. And third, record. Capture the log and the screen video. Providing the developer with this perfect, pristine digital crime scene is quite literally the only way to get a bug successfully patched on the bench.
I want to take a second to reflect on this powerful quote from our sources. A successful OTA update saves a trip to the dealer. A failed one costs a car. I think this perfectly summarizes the incredible responsibility that QA engineers carry. Every single day on the test bench, they are ensuring that these multi-million-dollar platforms are completely resilient. They are in the trenches, battling simulated bad Wi-Fi, corrupted files, and massive power drops long before the vehicle ever reaches a consumer.
So, what does this all mean for us? Are you ready to become the final line of defense before a car hits the road? I really hope this explainer inspires you to look at your own vehicle's dashboard just a little bit differently the next time you turn the key or, press the ignition button. There is a vast, hidden digital architecture working tirelessly right behind that screen. Thanks so much for joining me on this deep dive, and as always, keep learning.